two wooden planks, 150 millimeters by 50 millimeters each, are connected to form a T-beam. A T-beam is a beam whose cross-section is in the shape of a T. So we call it a T-beam. T-beam. If a moment of 3.4 kilonewton meter is applied around the horizontal neutral axis, find the stresses at the extreme fibers. So the stresses we are calculating are the stresses at the extreme fibers, and the extreme fibers of this T-beam are, this is the top fiber and this is the bottom or the lower extreme fiber. Now, the first thing we are going to calculate is the position of the center of gravity of this cross-section T-beam shaped. Now, for us to be able to get the position of the center of gravity, we are going to use this table here, whereby we are going to have the component. Now we are going to divide this T-beam section into two parts. That is, when we divide it at this point, we are going to have rectangle 1 and rectangle 2. The center of gravity of rectangle 1 is this one. Now to locate the center of gravity of a rectangle, you just need to join the diagonals of that rectangular section, and where the two diagonals meet, that becomes the center of gravity of that rectangular section. Likewise to this one here, you join the diagonals, and where they meet, that becomes the center of gravity. Now we have two components here, rectangle 1 as well as rectangle 2. Now the area of rectangle 1 is going to be length, which is 150 millimeters, therefore 150 millimeters times a depth of 50 millimeters, which in this case is 7,500 square millimeters. Likewise, the area of rectangle 2 will be the breadth of 50 millimeters multiplied by a depth of 150 millimeters as well. Therefore 50 times 150, that is going to give us 7,500 square millimeters. Then we have the centroidal distance y from LL in millimeters. LL is this bottom fiber. Now the centroidal distance y from LL of rectangle 1 is going to be the distance from LL all the way to its center of gravity, and that distance is going to be 150 millimeters plus half of the depth of rectangle 1, which is 25, and that's going to be 175 millimeters. 175 millimeters. For rectangle 2, the centroidal distance y from LL in millimeters is going to be half of 150 millimeters, which in this case is going to be 75 millimeters. Then from there we have AY. AY will be the area of the two components. Therefore, for example, rectangle 1, AY is going to be the area of rectangle 1 times the centroidal distance from LL. Therefore, 7,500 times 175, 1,312,500. Therefore, that is 7500 times 175. 7500 times 75, that is going to be 562,500. Then we are going to add AY. Therefore, when you add AY, that is going to be 0, 0, 10, 0, 1, 5, 7, 8, 1. Therefore, we are going to have 1,875,000. And then we are going to add the area of rectangle 1 plus area of rectangle 2. That is going to be 15,000. 15,000 square millimeter. Now, we want to get the position of the center of gravity of now the whole T-beam section. And for us to get the center of gravity, we are going to say bar Y. Bar Y is the distance from LL to the center of gravity of this T-shaped beam section. Therefore, bar Y is going to be summation of AY all over summation of A. Now, summation of AY is the summation of, or is the sum of AY for rectangle 1 plus AY for rectangle 2. That is giving us summation of AY, which in this case is going to be 1,875,000 divided by 15,000 divided by 15,000. Now that's going to be 125 millimeters. Therefore, bar Y is going to be 125 millimeters. Therefore, it means that the position of the center of gravity of this T-shaped section of the beam will be 125. If we try to approximate that position, this is 75 millimeters from LL. The whole of this one is 150. Therefore, 125 is about that point. Therefore, that is the center of gravity of this T-beam. So we have the center of gravity, and at the center of gravity of this beam, that is where the neutral axis is going to pass. Therefore, the neutral axis usually passes at the center of gravity of a given section of a beam. Therefore, this distance is 125 millimeters. 125 millimeters. The remaining part is going to be the whole of the depth of this T-beam section of the beam is 200 millimeters. 200 minus 125, that is going to be 75 millimeters. Now, the section above the neutral axis with a depth of 75 millimeters, that is the section subjected to compressive stress, and therefore we call that part YC, compressive stress section. The layer or the section below the neutral axis all the way to the bottom fiber, 125 millimeters, that is the section subjected to tensile stress, and therefore we call it YT. From the bending equation, we have this relation: stress over Y is equal to bending moment over I. Now, what we need to calculate is the stress. Therefore, we are going to make stress the subject of this equation. And this is going to give us stress is equals to bending moment multiplied by Y all over the moment of inertia about the neutral axis. Therefore, we are given the bending moment M, which in this case is 3.4 kilonewton meter. We have Y for both the compressive section as well as the tensile section. What we don't have is the moment of inertia about the neutral axis, and therefore we need to calculate the moment of inertia about the neutral axis. And therefore, the moment of inertia about the neutral axis is going to be given by B1 D1 cubed all over 12. That is for rectangle 1 plus the area of rectangle 1 into. Now, when we consider the distance from LL to the center of gravity of rectangle 1, that is 175 millimeters, which in this case is Y. And then the distance from LL to the center of gravity of this whole beam is 125 millimeters. Therefore, the distance between the center of gravity of rectangle 1 to the center of gravity of the beam, that part we can call it the elemental strip, will be Y minus bar Y, and then we square it. That is the formula we use to determine the center, the moment of inertia of about the neutral axis of rectangle 1. We are going to add that one to the center, the moment of inertia about the neutral axis of rectangle 2, which in this case is going to be B2 D2 cubed all over 12 plus area of rectangle 2 into bar Y minus Y, and then we square. Why bar Y minus Y? Because the center of gravity of rectangle 2 is 75 millimeters from LL, YT is 125, and therefore the distance from G to G2 will be by Y minus Y, and then we square. Now, the moment of inertia about the neutral axis will therefore be given by the breadth of rectangle 1, which is 150 millimeters, therefore 150 millimeters times its depth, which is 50 millimeters. Then we cube the depth, divide this by 12, plus the area of rectangle 1, which is 7,500, therefore 7,500 into Y is 175 minus Y T is 125, and then we square, plus that one of rectangle 2, the breadth of rectangle 2 is 50 millimeters, therefore 50 multiplied by its depth, 150, we cube it, we divide through by 12, plus area of rectangle 2, 7,500 into YT or bar Y is 125, therefore 125 minus Y, which is 75 millimeters, and then we got it squared in that form. And therefore the moment of inertia about the neutral axis. When we carry out all this calculation, ladies and gentlemen, we are going to have 5,312.5 times 10 raised to the power of 4 millimeters raised to 4, which when we convert the millimeters raised to 4 to meters raised to 4 is going to be 5312.5 times 10 raised to the power of -8 meters raised to 4. Therefore, that is the moment of inertia about the neutral axis. Moment of inertia about the neutral axis. Now, finally, we have the moment of inertia. Therefore, we calculate the stresses at the extreme fibers, and in this case, we are going to begin with the stress that is the compressive stress. Remember, the top fiber is subjected to compressive stress. Therefore, compressive stress will be given by the bending moment, that is a moment of 3.4 kilonewton meter applied around the horizontal neutral axis, around the neutral axis. So, around the horizontal neutral axis, a moment of 3.4 kilonewton meter is applied. So, that moment will induce stresses at the extreme fibers of this beam. Therefore, the compressive stress is going to be bending moment, in this case 3.4. It is in kilonewton meter, we convert it to newton meter. Therefore, 3.4 times 10 raised to 3 Newton meter multiplied by Y, in this case YC for the compressive section, which is 75 millimeters, converted to meters. That is going to be 75 times 10 raised to the power of -3. Then we divide this through by the moment of inertia about the neutral axis, which is 5312.5 times 10 raised to the power of -8 meters raised to 4. And this is going to give us 8 times 10 raised to the power of 6 newtons per square meter. When we convert 8 times 10 raised to power 6 newton per square meter to meganewton per square meter, we are going to have 8 meganewtons per square meter. Therefore, that is the compressive stress. The tensile stress, on the other hand, that is the lower fiber, the lower extreme fiber, it is subjected to tensile stress, and therefore the tensile stress will be bending moment about the neutral axis, which is 3.4 times 10 raised to power 3 Newton meter multiplied by YT, that is the section under tension, which is 125 millimeters, converted to meters, that will be 10 raised to the power of -3. We divide this by the moment of inertia about the neutral axis, 5312.5 times 10 raised to the power of -8. So this is going to give us 4.8 times 10 raised to the power of 6 newtons per square meter. Converted to meganewton per square meter, that is going to be 4.8 meganewtons per square meter. Therefore, ladies and gentlemen, that is how we usually calculate the stresses at the extreme fibers of any section of a beam, be it L beam section, T beam section, I beam section, and so on and so forth. Therefore, thank you for watching our video. Please don't forget to subscribe to our channel. Thank you.